So let's continue with our presentation, and here we have some set of slides comparing C code and assembly code. So this is high-level programming language. Increment the value. For majority of arithmetic operators, there is a corresponding assembly command. So for instance, plus can be applied as increment the specific memory location. This is moving things around places. So assignments in high-level programming language would typically look like a move instruction in assembly code. This is bitwise and applying some sort of bit mask to a variable, and here this looks like this. We have an instruction that is named end, which is bitwise end operation, and this is our mask, and this is our variable. And arithmetic addition is add instruction. So by the way, this addition is for integers and not for floating point data types. For floating point data types, we have a separate set of instructions. So longer expressions would look longer in assembler. So basically here you see that we have 1, 2, 3 add operations, but because assembler can only work with just one operand in memory, it requires some additional movements of the values before the arithmetics can be attempted. So this sum variable we load it from memory into one of the registers and then use this register as accumulator for all values. Initially it contains the value sum, and then we add x, y, and z, and everything gets accumulated in this variable, and then the assignment that is taking place at the end of this expression is also corresponding to this move instruction, which takes the result of all this accumulation and puts it back in the location of memory allocated for variable sum. So this is just a highlight of the kind of flavor, look and feel for assembly code, which corresponds to this, that now we can use a high-level programming language code as a pseudocode guiding us to in terms of like what this program does in assembly. So in the machine language, this is now in the hexadecimal format. These instructions that we just were looking at obviously are expressed in binary form, but here we kind of reduce the notation to just hexadecimal notation. So this is difficult to deal with. This is very challenging to debug and understand or disassembly as a part of the code. Of course, mnemonics of the assembly language simplify understanding, and mnemonics are pretty much the mnemonics of the commands. Simplify otherwise cryptic versions of these opcodes somewhere embedded in the actual binary instructions. So assembly is a significant step above machine language in terms of the readability. And also where these the addresses of variables are embedded somewhere in these instructions, here we can also use named locations in memory. In order to branch to a different part of the program, we have jump instructions. So typically we need to provide a label inside our code segment somewhere, and we can jump to that label, basically transfer control to that label by using jump instructions. So this one actually to two jump instructions demonstrating jump to the label at the bottom here, done. Jumps can be conditional, so we can compare values, and if, for instance, here this is a mnemonic of jump if equal, conditional jump, if the result of this comparison is such that basically the two values right here are equal, then we can jump to done label right here. So done is just an example of a label. You can have other labels in your program. Now this is extremely important page. This is a set of general purpose registers on Intel x86 platform that we're using here. So the registers are memory locations which are named memory locations, which are built into the CPU. So CPU has these registers already available to us. These are general purpose registers that we can use to store intermediate values and the values that we use to load information from memory and use them to store the values back in memory. So registers are scarce. There really aren't that many of them on 32-bit Intel platform, and so these registers are 32-bit size registers. For instance, EAX stands for Extended Accumulation Value, base register, extended base register, counter, and data. And so these are source index, destination index, base pointer, stack pointer register, and these are flags. So so we have a set of registers that allow us to store information. So to give you a few examples of this, if I say move for instance into register EAX, a value of 5. Okay, so this is value of 5. So we're loading this register with the value. So recall that in assembly, when the move instruction, basically when there are two operands, the direction is like an assignment from right to left. So this value 5 is loaded into this register EAX, and the entire register gets updated. Okay, so we can try this in our code. Our program right now does not interact with the user. So recall that I switched to debug mode. I will now build just to make sure that everything is built. Okay, so it gets built. And now we are ready to run this program, but it does not interact with the user, so I will insert the breakpoint. You can just right click here and say breakpoint. You can delete breakpoints, you can add new breakpoints, and so forth, or you can just click on the margin to insert and delete breakpoints. So if I now say debug, start debugging, the program should be loaded into debug environment, and it stops in front of this instruction. This arrow indicator shows us that this is the next instruction to execute. To be able to display these registers, we can go to debug windows, and there is a window here which displays the current content of these registers. So these are my registers, and you can see that my EAX register is right here. It's loaded with some sort of memory address, but I don't care. I am about to change it. So if I step over this, you can say debug step over. Okay, so or press F10. If I step over it, you can see that the register has changed, and the instruction pointer also went forward to the next instruction, but this move instruction has updated this register in memory. So we have a combination of these registers, and let's see that what are the uses of these registers. So this is the actual display of my registers right now. I press Control down and drag my mouse to undock this, and so we can use it closer to you can even change the size of this window to make them display more or less in one column. So we have EAX, which is accumulator for operands and results. Also, when you're returning a value from a function in C, the result is loaded into this register. EBX is a base pointer to data in the data segment, but also can be used for any kind of arithmetic operations. ECX is a traditionally used for counter of loop operations, but in addition to this, in C++, C++ compiler will store this pointer pointing to the current object in memory in register ECX. So this is a very special register for C++ programs. EDX is a data pointer, or simply the location of the data. Frame pointer useful for stack frames. So when we start making procedure calls or function calls in C++ or C program, of course local variables have to be stored in a stack frame, and that stack frame typically needs to be built and prepared in the on the stack, in the stack memory segment. So base pointer allows us to point to the original location of the stack memory. Stack pointer is another register that deals with stacks. So these two registers, ESP and EBP, typically used together. So these are the current memory addresses that they're pointing to. ESP register simply points to the top of the stack. So what happens with the stack is that when you have the stack memory, it's just an area of memory like this, okay, and the stack pointer always pointing to the top of the stack, okay, and the bottom of the stack. So this is your stack frame, and the bottom of the stack is typically loaded into this register right here. So you can see that if you compare my base pointer, all right, so this has a lower memory address compared to the stack pointer. Okay, so these are registers that we use to work with the stack. And when we are using loops and inside loops, of course, we have often variables like index or subscript value or some sort of counter that could be used as array index. So we need some kind of indexing when we need to work with blocks of data or arrays of data. So there are two designated registers that can be used by instructions as a source index and destination index, and these are ESI and EDI. EIP right here is our instruction pointer. We cannot change it directly, but if we try to use a jump instruction, those instructions will be changing instruction pointer to a different location where you want to jump. And flags right here, these are my flags, is the result flags of all sorts of conditional operations. Like for instance, when we compare values, these flags are updated so we can know what were the results of these comparisons. Right, so these are the registers, and basically their sizes can be used such that, for instance, right here I move the value 5 into this register. So the entire register EAX, which is 32-bit size register, from 0 to 31, these are the positions of the bits inside this register. When I move the value into register EAX, as a result of this move instruction, this entire register is updated with value 5. Okay, but it's possible to say AX, and if I use AX, only this portion of the register, the lower portion of the register, will be updated, because it's a 16-bit AX register. And finally, there are two more parts of register EAX that I can update. If I say update AH, then this 5 will be stored in this portion of EAX register, which is only 1 byte size. And so we can also use AL, which is this part right here. So if I say move 5 into AL, then this portion of the register will be updated, and this part will not be updated. It will just remain the way it was prior to this operation. So you see that there are parts of the register addressable by move instruction, and so the registers have basically they all have these parts, and you can use AX, BX, and so forth, like for instance DI and SI, which correspond to the 16-bit size register inside extended register. So AX is 16-bit and EAX is 32-bit, but it's really the same register. And if you're updating AX, you're definitely updating part of register EAX. For now, we'll be just using the entire 32-bit size registers, and when we work with characters, we may start using 8-bit size registers, basically 1 byte size register.